All right, so thanks everyone for joining us today. I hope you all had a great week. Today we have the pleasure to host Irina, who is a prof at Mila and who will share with us some thoughts on scaling laws for foundation models. One of her students, Ethan, will also present the last part of the talk. So before handing the mic over to you, Irina, let me remind you all of some house rules. As usual, clarification question will be allowed to be asked during the talk. If you have a question, you just have to type the word question or I have a question in the chat. And when the time is right, I'll let you directly ask it. And there'll also be some additional time at the end of the talk for people to ask further questions, make some comments, or have a more informal discussion with Irina, Ethan, and everyone else. That's pretty much it for me. Whenever you're ready, Irina, the floor is yours.
Thank you. Well, thanks for inviting me again. As you mentioned, the talk has two parts. So I'll do some kind of introduction and a bit of history and modern developments. And then Ethan will talk in a bit more detail about our recent paper on scaling laws. So let me start with very high level slide. As probably many of you been around the debates last year at Mila, and not just at Mila, about defining AGI, whether AGI is a goal of our field, what AGI is, and so on. There have been lots of discussions, but in a sense, at higher level, many agree that the motivation in the artificial intelligence field is building artificial general intelligence, whatever they mean by that. Of course, the opinions kind of vary quite a bit, from creating a conscious being to something very mundane as a multitask system that is just able to generalize well. So in our work, we kind of just try to keep it maybe somewhat more kind of practical and essentially stick to the definition of AGI with a kind of focus on the word general. And general means generalization, well, to a wide range of different tasks and domains and applications and so on and so forth. So at high level, like whenever we say AGI, we essentially mean definition, well, again, not very formal, but given on OpenAI web page, that you're trying to build systems that are going to be highly autonomous. And at the same time, they will be able to do such a wide variety of useful tasks that they will be at human level or outperform humans on this large set of, we can set all economically valuable work. So it's, again, not a precise definition, but you kind of get the idea. And it's all kind of, if you take a step back and think about the whole history of even statistics and later machine learning, and of course, AI and its application, it's always been about generalization. I mean, it's always been the holy grail. And in classical statistics, it all started with curve fitting and trying to extrapolate and assuming that even if the data are identically and well, basically independent, identically distributed, but you only see a few points, can you extrapolate to the new unseen points? Then, of course, for applications in practice, whether it's like medical, where you switch from hospital to hospital, or it is any kind of robotics applications where environment changes and the list goes on, generalization need to be from kind of one domain to another, so it becomes more of out of distribution. So data distribution starts changing more drastically. The distribution of say, if it's classification problem, the conditional distribution of your class given the data may change too. This can happen sequentially, and then you get continual learning. Or it can happen kind of simultaneously, and you have multiple examples of different data distributions. You're trying to learn from all of them simultaneously. So later on, you will be able to have like a generic model that's easy to adapt to any new data that might not be necessarily what you trained on. So meta learning. Transfer learning is essentially kind of a concept that always appears in all these fields like continual and meta learning, domain adaptation, and so on. It's all about the ability of system to generalize way beyond its kind of training data, and how far beyond the transfer should go. That's essentially kind of the question. And until recently, I mean, all these fields, we are asking pretty much the same question in different settings. Until recently, it was a very hard question because essentially, you needed all kind of heuristics to, for example, in continual learning, to make sure that you adapt the model to new data and it doesn't forget old data, so on and so forth. There are many methods proposed in out-of-distribution generalization. So this question was definitely not new, but the solution that kind of emerged in the last couple of years may sound a bit dumb or straightforward or brute force, but nevertheless, it appears to be solving many of those problems. And the solution is essentially scaling the amount of data and, of course, the amount of information in the data. Data should be diverse enough, because even if you have billion of samples, which are just copies of the same sample, you're not going to learn much. But it's assumed that real life data are diverse enough and representative of kind of situations that you may need to kind of learn about in order to kind of work well later. Then not only data should be scaled, but the capacity of the model. Essentially, what you're talking about when you're talking about scaling is at its core, scaling the amount of information in the data and scaling the model capacity to incorporate that information. And if it's done properly, then essentially you may end up learning kind of a principal components underlying the data distributions in the world that you will have to act in. So at proper scale, you may actually almost grok the world, and after that, you might be able to generalize out of distribution quite well. Again, this is kind of making assumption that our world has is well approximated by some finite set of components or mechanisms or kind of essential blocks of knowledge. And if you scale enough, you can kind of grasp it. In any case, this kind of goes back to the classical kind of short position paper that many of you might have seen, the bitter lesson. And it's very simple kind of lesson in a sense, if you think about that. But essentially, it says that if you look at the whole history of artificial intelligence, remember how it started. It started like rule-based systems, like specific rules for specific tasks, specific features, expert kind of designed features for particular domains, be it images or audio or language. And all the systems kind of worked at that level of specifics. People were trying to find smarter and smarter kind of ways of extracting those features manually. And all those methods are now completely replaced by automated feature extraction. Well, as we all know, deep learning, right? And large amounts of data. So none of these rule-based systems are really that relevant anymore. And the trend continues, if you kind of look at that. And essentially it continues because more and more compute becomes available. And if you use generic methods such as search and learning at massive scale, then those statistical methods seems to keep outperforming all the kind of expert knowledge-based type of approaches. And that kind of raises a philosophical question, because when you approach your research and start asking questions, what should I work on? It's important to keep in mind, like whatever you're working on right now, will it be still relevant, I don't know, 10, 20 years from now? Say people who worked on the rule-based expert system spent quite a bit of effort and published quite a lot of papers on that. Nobody really kind of uses it right now. So why is it important? I mean, one can say, well, we can research anything and work on anything, but you need to keep in mind that the time and resources are limited. And if you choose to work on something, it means you choose not to work on something else. So basically you need to choose smartly. And this is, as I said, just a generic kind of philosophical outlook, which kind of motivates the recent scaling revolution, because examples are multiple. Computer chess was played by programs that encoded expert knowledge, only to be kind of made obsolete by pretty much like brute force, stupid, massive, deep search because of more compute available. And with computer Go, well, search, self-play, again, relatively generic approaches without too much of specific domain knowledge, but done at scale with larger compute. And examples go on, and speech recognition, computer vision, language processing, all those handcrafted features were replaced by deep learning and more computation, more data, basically statistical approaches. So what does it essentially tell us? And why the lesson is bitter? It's bitter because people definitely spend lots of time on designing those specific methods and putting our expert knowledge in the system. The paper kind of asked us to rethink it and perhaps think not about putting our final result of kind of evolution of knowledge in the system, but rather try to create systems that can evolve and end up with useful knowledge, which may or may not be necessarily exactly same way and may not necessarily end up with exactly same, say, brain architecture or same kind of results as we did. But that's kind of important approach, important take to keep in mind. And that goes well with all these recent advances as we, I mean, we can spend hours just talking about all recent systems that were based on this principle of scaling and keep kind of progressing as we speak, almost like every week, if not every day. Language processing, ChatGPT, the ability to generate text improved drastically, even though you can criticize mistakes, factual mistakes, and perhaps not always nice behavior, but everybody would agree that none of the natural language systems a few years ago was capable of doing that. Generative AI, like Stable Diffusion and other models, like just all modalities, music, you name it. So all those kind of recent advances, literally in the past 2 years, that kind of growing exponentially, they all based on the approaches basically based on scaling in terms of data, in terms of model size, and in terms of compute. And the term was coined a couple of years ago. Well, we can call them foundation models, but essentially the idea is if you, instead of trying to solve your specific problem and train, say, supervised classification method or whatever specific reinforcement learning method for specific game or whatever your specific problem is, if you try to pre-train at large scale over large amount of diverse data in unsupervised manner, a model that's large enough to incorporate this information, it can serve as foundation for multiple subsequent or downstream tasks. And whatever the criticism about the name and rebranding, I don't know, but I think foundation model kind of makes sense. It both serves as foundation for future systems. It incorporates knowledge and patterns in the domain that can be later on used and utilized by specific kind of systems and fine-tuning towards your tasks. At the same time, of course, it's not a final product. Like GPT system is not a final product. You need to do things on top of that to make it useful, so on and so forth. So it's foundation in a sense. And the examples go on. I probably don't even have to list that because, yeah, by now everybody knows about all kind of modalities and all kind of recent successes. But GPT-3 was perhaps kind of the breaking point on the scaling of the AI research, and Ethan will talk about the breakpoints later in the second part of this talk. But yeah, the list of systems that are based on kind of foundation model approach and pushed state of art recently grows very fast. So as again, pretty much all of you probably know by now, the advance of GPT-3 versus GPT-2 was not in invention of any new architecture, but essentially in scaling the model and data size by orders of magnitude. And GPT-3 is essentially an autoregressive model that predicts next token given previous set of tokens, and that uses this quite simple but successful transformer architecture based on attention. And attention essentially allows you to have a long window of history and choose what's most appropriate there, and kind of avoiding issues with sequential processing that LSTMs used to do. There are still limitations, of course, that you're bounded by your window, by your context, and you still need to figure out how to make memory of those systems larger or more kind of effective. So they will be able to remember conversations, not just like a current conversation, but also conversations with other users and with you yesterday. So memory augmented large-scale systems is kind of topic of research these days. But essentially, the improvement in performance, as I'm saying, was primarily just due to scale. And examples go on. That was just kind of example of CLIP, which was actually a smaller transformer, but it was for image and text, outputting text given image. The thing is that it's out of distribution performance of zero-shot generalization was remarkable comparing to their state-of-art systems. So in a sense, that really was kind of solving the out-of-distribution generalization problem in this domain. So on and so forth. And the classical type of picture from the original GPT-3 paper, where essentially the claim was that those large-scale models become few-shot learners. So they are able to generalize out of distribution to unseen tasks, to a wide variety of them, because they accumulated enough of patterns from diverse data and were large enough to be able to accumulate that. So the plot was showing the kind of huge difference in the ability of the model to solve problem in terms of accuracy when scaled from roughly a couple of billions to like almost 200 billions, 175. So anyway, so this is good. Yes.
We have a question from Jim.
Okay, so I'm opening the chat.
I think he'll ask it directly. You can ask it directly.
Sure.
I can speak if it's okay. So it's about a few slides about the bit relation. So is it possible that the examples given the bit relation is kind of biased? Maybe these problems solved happen to be those that can be solved in pure data-driven or computational-driven manner. And also, can large-scale pre-trained models help to discover physics laws, where I think the humans' intelligence is, or like this kind of smart ideas will play a significant role?
I didn't completely capture the last question, but when you say that the take is biased, the take was generalization over several domains. So the examples were given there, but usually the rule of thumb is, and I'm coming from applications of machine learning to, say, brain imaging and biology. Like I spent years doing that. Data sets in such fields are usually very small. So you either don't use deep learning and use something like SVM and regularized regression if the data sets are extremely small, or if they're medium size, you can use deep learning, but you have to put lots of regularizers there as well. And usually, whenever you have relatively small data, in order to do well, you need regularization or prior or human knowledge. And it's true that human knowledge helps up to the point. So the point is that when you have either lots of data available in this domain, or you can build large-scale models in different domains and transfer, then perhaps you will not need to rely anymore on those specific regularizers, inductive biases in that knowledge. And the reason why it actually might be even hurting you, because if those priors are not quite correct, and you should have been relying on the patterns in the data. Once the data are available, maybe you better trust those data. And you try to simplify your model to kind of eliminate unnecessary biases. I can show later picture, and Ethan will also have an example, a classical example of, say, convolutional networks versus vision transformers. Convolutional networks do incorporate bias in the architecture, like the convolutions, how the vision system works, and they were working great for a while at relatively small data kind of regimes. Vision transformers were not nearly as good, but at the very large scale data regimes, the situation reversed. And the reason for studying scaling is to know what works best in what regime. So you can decide whether you have like enough data to use more generic, or you have to use more specific approach.
Okay.
So it's kind of a trade-off. So ideally, the scaling laws should be showing you everything that happens from low data regime, medium data regime, large data regime. Similarly with model size and compute, like if you don't have much compute and so on, you do what you can. But another point is that perhaps it doesn't have to be just your domain. And I know I probably need to continue, and so Ethan will have time to present scaling laws. What I'm trying to say is that it's very interesting recently that people are able to transfer models across domains, and it raises questions just how far the transfer can be pushed. If you train a successful language model and can adapt it without much change by freezing internal layers and only changing kind of inputs and outputs and maybe adapting them to images, and it works well, like in that paper on the transformers universal compute engines. And if people can train on video from YouTube and transfer to fMRI, like Danilev's doc and his co-authors had this paper. So once you start training on large scale data one type and transferring to the other type, well, I guess assuming there is some commonality in high level concepts in those domains or something, it again kind of raises a question that maybe in domains like biology and brain imaging, you shouldn't be relying too much on, and the core question is how much is too much, on the prior human knowledge. Maybe you need to build on top of those systems and fine tune using your small data from your domain. To be explored, but it's something to keep in mind as, I don't know, sanity check when you're trying to do something, like whether it might be later on solved by simply scaling once more compute becomes available or more data. Anyway, it's a very interesting question, but I do need to continue. So we're almost at the 30 minutes, and I really would like Ethan to tell you more details about recent developments with scaling.
Okay, thank you so much.
Okay, anyway, so I'm kind of just glancing through you. Many of you probably read the paper, or if not, that you should definitely read the original GPT-3 paper and the subsequent scaling laws, like the classics by now. But the point was that the results at large scale, at multiple orders of magnitude in terms of compute here, or in terms of, in the previous slide, I'm going forward. Yeah, so in terms of data on x-axis in this example, increasing by orders of magnitude, or in terms of compute in this example, the y-axis, which is performance, basically would improve with scale. And the interesting observation was that, I mean, if you consider the best achievable performance varying other parameters in the model, just with increasing compute, you could see that loss was falling as power law. And the power law is straight line in log-log plots. Yeah, power law is like a polynomial, basically, power a times x to the power of b. In log-log, b becomes the slope. So those observations were kind of later summarized in this by now classical paper by Jared Kaplan and his authors, where they actually showed scaling laws following power law at least in the experiments that they ran, which as later turned out, I mean, there are more interesting cases that do not fall in the power law. Again, Ethan will talk about that. But at least in their experiments and many others, quite often, their performance, such as, for example, test laws, would fall as a power law or as a linear function in log-log, given compute data set size or the number of parameters of the model. And these plots, essentially, the way they should be interpreted is that the other two parameters, say, given fixed compute, if you are allowed to play with data and the number of parameters and choose the best combination, then the resulting scaling law will be, well, power law given in this kind of first plot. Just a bit of a spoiler alert. It could be done more efficiently than this power law, and it was discovered about a year later in the so-called chinchilla scaling laws. But it was still kind of power law, just more efficient. With data set size, same thing. If you have certain fixed amount of data, but allow yourself to try different size of the model and spend different amount of compute training that, perhaps you can do multiple epochs or not, the best result plotted will follow power law as well, although with different exponent. Same turned out to be true. Basically, I'm just kind of very briefly summarizing that classical paper by Jared Kaplan that many of you have seen by now, which is kind of listed here. So this was all great. And back to the question that was asked earlier about human knowledge, inductive biases, or specific architectures. That was a classical example. And I think Ethan will also mention that from this paper, where the vision transformers, while being kind of suboptimal at relatively small data regimes, letting convolutional networks kind of work best, outperform convolutional networks later at the larger data scale. I'm probably not going to have that much time, and I'll just glance through so we can go into details on the recent work. But I just wanted to say that actually neural scaling laws in deep networks date way back before Jared Kaplan's actually paper. And to the best of our knowledge, well, thanks to Kartik, who pointed to this paper, one of the first papers which discovered power law scaling in neural networks was this paper by Irina and her co-authors in NeurIPS 1994. So essentially, it was perhaps the first paper we could find that had the power law for the DeepNet loss function. Later on, Ethan will be talking about several functional forms proposed previously and showing how a new recently proposed functional form outperforms them. But essentially, notation will be that basically simple power law is M1, power law plus constant M2. And there was also another more recently proposed extension of that in prior work, not in ours, we compared to. So this is just example of the same point that convolutional networks and vision transformers were making, just made in 1994. So precisely the point that Irina and co-authors were making is it's important to study scaling laws, because look at this hypothetical plot where you have several classifiers and your test error seems to be better for one at low data set size scale. When you increase the data set size, situation may reverse, and you need to know about that. It's because you may get more data and you may get more compute in the future. You want to know what methods to invest in. So scaling laws are investment tool for machine learning researchers. Anyway, so they also showed, as I said, power law in log-log scale for the case of data, fully connected networks. Then there were more papers on the topic, 2017. Joel Hasnas, who was at Baidu at that point, and he basically studied with his co-authors what happens with training data scaling. They discovered a bit more kind of complex behavior. Again, Ethan will talk about the functional form that can kind of capture that all. initial regime of slow learning with insufficient data without much improvement, a breakpoint that goes into more rapidly learning regime, which looks like power law region, and eventually asymptotic, not being able to kind of go lower than certain irreducible error, which say in classification case may be known as a Bayes risk. In unsupervised case, it's just like irreducible entropy. And there were more papers later on, and people were trying to come up with alternative functional forms for scaling that would capture more precisely the behavior performance of deep networks beyond just plain vanilla power laws, and applying them to different setting, whether it's compute, data, or model size. So Jared essentially and his co-authors, they showed that power law also applies to compute, not just to data and model, as people showed before. And they used those laws for very practical purpose of deciding which particular engineering kind of approach while training GPT-3 would scale better. So it was not just like kind of for academic curiosity, but indeed they use it as investment tool, deciding where to spend more compute so they will get better improvement in the loss kind of for which method. Anyway, so I was just kind of listing a few papers which are all in the related work of our recent paper that Ethan gonna present. But yeah, there was quite an interesting history and progress has been made, but unfortunately until recently, there was no single functional form that could really capture all non-trivial behaviors. And non-trivial behaviors include sometimes rapid changes in the rate at which performance improves. Classical picture from GPT-3 paper where on specific task on the addition, well, in this case, like n argument addition from 2 to like 4 and so on and so forth. You see that when you grow the model size for a long time, GPT was not able to learn arithmetic, but at sufficient size of the model, it would suddenly kind of grok it and have this transition in performance. Then people also observed this type of groking behavior when the x-axis was compute, while model and data were kind of fixed. And that was this groking paper from OpenAI from iClear 2021. So that definitely looked very interesting and happened by accident because the authors forgot to kill the process and thought that, I mean, there is nothing interesting going on for a while because the accuracy of learning, similar to arithmetic task, it was also a table describing binary operation, that it was not really learnable. And at some point, apparently the search found place in the loss surface where there was a quick jump from very bad solutions to very good one. And that's what happened first with training loss and then with test loss. And they called it groking because at some point the system just understood suddenly or groked the problem. And the examples of this non-linear inflection point kind of having behaviors started appearing in more and more papers. This paper did a really nice job summarizing empirical findings in multiple other papers about the emergent abilities of large language models. So these behaviors where the transition and performance would suddenly kind of change the slope and then you kind of almost see the inflection points. It's happening on multiple different tasks in multiple different data sets with multiple systems. So Ethan's going to talk about that in a minute, but essentially this is just a one slide advertisement that the question was, can you come up with a functional form that can capture all this variety of behaviors and more? Because apparently previous functional forms were insufficient. So that was kind of the motivation. In any case, let me just wrap up and Ethan will tell you more details about kind of the functional form and the results. Basically, all I want to say that this progress with large-scale models and achieving state-of-art results essentially requires a lot of compute, right? And the question is, how do you get this compute if you are not working in OpenAI or Google or DeepMind, and if you're either in academia or you in various open source organizations? So it kind of generated the whole movement of open source AI communities trying to get compute in different ways and trying to like build those large scale systems that would be fully open and fully available to everyone. And also doing the same thing with data sets on which they can be trained. So open source, open data, alternatives to all these state-of-art proprietary kind of models. And one path to that was to apply to large-scale kind of compute at supercomputers. So very briefly, I'll just mention that we have an ongoing project because we applied with in collaboration with several open source communities such as Lion, Luther, and others for Summit, US supercomputer. And hopefully next year they will make Frontier available, which is even larger one. So it was kind of a way for academia and open source to get their hands on sufficiently a large amount of compute, even though it's not matching maybe the compute available in industry, but it's definitely more than anything we had available before. The collaboration is growing. It's besides Mila, University of Montreal, as I mentioned, Lion is a German nonprofit organization focused on open source models and open source, open data. And also, well, AI Sweden, Luther AI, and others. And this is the name of their current project on Summit. It's part of the so-called Insight program. If you're interested, I can provide more details. We have Discord server with several projects on that, but essentially the key projects include building a suite of language models to study scaling, to study compare different architectures, to study how scaling improves different properties such as continual learning and so on. The second kind of part of the language model project is studying how fine-tuning can affect behavior of the model, which is a very hot topic these days with ChatGPT and Bing, obviously. The multimodal language vision models and Align Chat Magma are basically in the category of interactive, human feedback-based or chat multimodal models that combine, in this case, images and text. And the larger, but kind of a bit in earlier stages project is developing also interactive, but highly multimodal generalist agent, think like OpenGato or something like that. Anyway, so I will skip some promising results on Summit, but bottom line is just showing that, say, the GPT NeoX is scaling effectively with number of GPUs. So that's good news. And same things seem to be happening with OpenClip, but those are more technical details. In any case, so the long-term goal of these collaborations is to be able to build large-scale systems by kind of obtaining compute on government-supported supercomputers, which are not just in the US, they're in Germany, Jewels, and in France, and in Japan, and so on. So by building this kind of multinational collaboration and obtaining compute on multiple supercomputers, we have a chance of staying at the level of the state of art that currently industry is pushing. So that's a hope. And the idea of democratizing AI so that models and data they were trained on will be fully available, and we know at least like what to expect and how to kind of affect their behavior. So it's double-edged sword. Anyone has access to that, but on the other hand, we believe that it's safer this way than when it's completely proprietary. Anyway, I'm done, and Ethan will now share his screen and tell you more about the recent advances in neural scaling laws based on his paper called Broken Neural Scaling Laws. Okay, So Ethan, can you
Yep.
share the screen?
Okay. Okay, can people see the screen fine?
Yes.
Okay, yeah, so today we're gonna talk about, well, I guess, there's the chat there. I can't see the chat, but oh well. Okay, so today we're gonna talk about broken neuroscaling laws, a paper with me, Shittich, Irina, and David Kruger. Okay, so AGI. There's a bunch of definitions of AGI, but one that's relevant is highly autonomous systems that outperform humans at most economically valuable work. So there's multiple paths to AGI. However, the only path that matters is the fastest path, because economic military competition is selecting for it. And as a result, it's the path that will be deployed in the real world. If one wants to steer AGI to be maximally beneficial, identifying the fastest path as early as possible is critical. Okay. Oh, yeah. So the fastest path to maximally beneficial AGI is that which scales best on all downstream evaluations that matter approximately simultaneously. So what you end up with is a plot like this, where on the y-axis you have performance on all downstream evaluations. This basically corresponds to like capabilities and alignment. Now on the x-axis you have the bottleneck at any point in the AGI timeline. So, and at least in my opinion, it's probably going to be compute for capabilities and data/measurement for alignment. So let's look more at the x-axis from this plot. So the bottom, so in this paper, the bottlenecks, i.e. the quantities being scaled on the x-axis that we look at, are the number of model parameters, the amount of compute used for training, the training data set size, and the upstream performance. In this left plot right here, like these plots are some estimates from this company called Epoch AI on how these bottlenecks will vary over the coming years. So on the left plot is an estimate of how much compute will be used for the largest training run each year. Like that little red triangle at the bottom left is how much compute GPT-3 was used for training GPT-3. And then on the right is the estimate for how much data will be available to the most capable organization in each in each year. So it's basically like estimates of how much high quality and low quality language data there will be, and estimates for how many frames of video there will be. Yeah. So yeah, let's look at the y-axis from this plot. So in the paper, all the metrics listed on the left right here these are all the metrics that we empirically investigate in this paper. So prediction error, cross entropy, calibration error, blue score percentage, reward, ELO rating, FID score, downstream or upstream, zero shot, end shot, or fine tuned, prompted and non-prompted. Yeah, so just when I say like a performance evaluation metric on the y-axis, I'm talking about things that people in the machine learning community are usually familiar with. Okay, so one might naively think that models that perform best at smaller scales, that the model that performs best at the smaller scale is the best heuristic to use when trying to figure out like which thing will be the best in the future. But that's a bad heuristic in my opinion, because often things that are the best at smaller scales are worse at larger scales. Okay, so then the question becomes, what characterizes this relationship between the x-axis, i.e. the quantity being scaled, and the y-axis, the performance evaluation metric, such that we can extrapolate, predict what the value of y will be for any given, i.e. larger, value of x? In this paper, we say and show that it's this equation right here. And on a plot, this equation looks like, on a log plot, the equation looks like this. So how exactly does that equation map to this plot right here? So N in this equation represents the number of breaks, i.e. transitions between n+1 consecutive approximately linear segments on a log-log plot. So like the purple lines in this plot right here are where all the breaks, i.e. n, happen in this plot. So like here, there's 3 breaks, and they happen around like 10 to the 6, 10 to the 14, and 10 to the 20. A is the limit as to how far like the performance evaluation metric can be like optimized, even if you send values of x to infinity. So it's kind of like you can view it as kind of like just the physical limit of the system. B is the offset of the functional form on a log-log plot, and it's analogous to the intercept B in y equals mx plus b on a linear plot. C represents all of the slopes of these lines. So like C0 is the slope of the first portion of the black line. C1 is the slope of the second portion of the black line. C2 is the slope of the third portion, and C4 is the slope of the C3 is the slope of the fourth portion. So like the actual scaling behavior is this black line. These colored lines that overlay the black line is to like indicate like it's scaling with a power law of this slope during that interval. And D tells you where will these transitions happen. So basically D literally is the x-axis value that where like the purple line intersects with the black line. And then F tells you how sharp are these transitions between these different slopes. So like for the first transition, F is pretty large, so that means that the transition is pretty slow. So you end up kind of with like a smooth curve. And then for the second transition, F is also large. So the black line has kind of like a smooth transition between the two slopes. But then on the third one, during the third transition, F is very small and non-negative. So the transition is very sharp and jagged looking. Okay, so here are the results. These are all the scaling behaviors that we've shown broken arrow scaling laws accurately model and extrapolate. Downstream and upstream, large scale vision, language, audio, video, diffusion, generative modeling, multimodal learning, contrastive learning, AI alignment, robotics, set distribution generalization. Yeah, it's a bunch of stuff, and we're gonna show plots for all these in a second, but it's basically everything that I and other people could think of. Yeah, and these are all the architectures that we've tested on so far. Okay, so yeah, so let's first talk about results for extrapolating the scaling behavior of large scale vision and language. So we tested on various architectures, residual networks, MLP mixers, and vision transformers and language transformers. The pre-training data sets were subsets of JFT300M and large amounts of text from the internet, so like hundreds of billions of tokens / words, and each is evaluated on a large number of downstream task evaluations. So basically there's like 100 downstream task evaluations that we looked at, and these are the functional forms from previous work that we compared to that Irina mentioned during her slides. So M1, M2, M3, M4. Yeah, so when you compare broken arrow scaling, the extrapolation of broken arrow scaling laws for downstream image classification and downstream language tasks, it basically like dramatically outperformed, like it outperforms all the previous functional forms the majority of the time. Like, and this is like when it's like having to compete against all 4 functional forms simultaneously. So like if any of the functional forms beat it, like it doesn't get that percentage score. So it's like almost like a 4-on-1 like evaluation where it had to beat all 4 of them to get a percentage point. Yeah, so, and this was like this is across like 100 different downstream tasks. Okay, so you're about to see a bunch of plots, and all these plots, black points are the points used for fitting a broken Earl scaling law. Green points are the held out points used for evaluating the extrapolation of a broken Earl scaling law fit to the black points. And a red line is the broken Earl scaling law that has been fit to the black points. 100% of the plots that you're about to see contain at least 1 green point for evaluating extrapolation. Except when stated otherwise, the interval of the plot contains 1 break of a broken Earl scaling law fit to the black points. Okay, so yeah, so broken Earl scaling laws, they accurately extrapolate the scales that are orders of magnitude away, even downstream. So this is, you pre-train on JFT 300M, which is like 300. It's basically like, you know, ImageNet, but like 100 times bigger, or something similar to ImageNet, but 100 times bigger. And then you do 5-shot fine tuning. And then the left is 5-shot fine tuning. The right is 25-shot fine tuning. And yeah, it basically like perfectly extrapolates an order of magnitude away what the test error rate is on that downstream ImageNet data set. And this is with, the architecture was MLP mixers, but it doesn't really matter what the architecture is. Like you end up with some results for everything. Yeah, and so then here's reinforcement learning, single agent and multi-agent. The top row is the fit and extrapolation for multi-agent reinforcement learning with compute, dataset size, and number of parameters on the x-axis respectively. On the bottom is single agent reinforcement learning with compute in the left plot and dataset size on the right plot. And like the algorithms are alpha 0, phasic, policy gradient, and PPO. Yeah, so it has really good fits and extrapolations for reinforcement learning too. Here's some results for diffusion generative models of images. On the left plot, the y-axis is FID score. On the right plot, the y-axis is negative log likelihood. So yeah, it yields good fits and extrapolations for diffusion generative models of images too. Here's extrapolation results for generative models of video. In this, like the video architecture, it's a transformer that receives VQ, VAE tokens as input, and yeah, it models and extrapolates the test cross entropy of generative models of videos very well. And the x-axis in this plot is compute used for training. Yeah, this is probably one of the most impressive plots in my opinion. So these plots are from the GPT, like the experimental data of this, it's from the GPT-3 appendix. So you fit the broken Earl scaling law with the first like smaller 7 model sizes from GPT-3, and then that green point on the far right of each plot is the like 175 billion parameter GPT-3 model. And then this is like the performance on all these downstream evaluations, and like it extrapolates them very accurately, even for like really steep jagged stuff like 4-digit addition in the like in the top left plot. Yeah, it also works fine with AI alignment. So this is from an Anthropic paper of like a large language model. And also notice the y-axis is ELO score, so you can kind of have kind of wacky like evaluation metrics, and it seems to work fine even with wacky evaluation metrics. Yeah, so this is a large language model fine-tuned with reinforcement learning from human feedback to be helpful, i.e. aligned, and the x-axis number of model parameters, and it extrapolates the performance at 80 billion parameters very well using smaller models to fit the broken Earl scaling law. It also works well with continual learning. So in this setup, you train a model on task A and then keep training on task B. Like you train on task A and then task B in sequence. And then, so like you're trying, at least supposedly, to make it forget about task A. And we take the mean of the test error rate on task A and task B. It follows a broken arrow scaling law and can extrapolate to the green point. And here's results for robotics and out of distribution generalization. So in the top left plot, in the bottom plot, the test set, it has held out colors. So like it basically has to like generalize to out of distribution colors. And like Birkenau scaling laws models and extrapolates its scaling behavior fine. And on the right plot is just a version where there isn't out of distribution generalization, which is just in distribution generalization, because there are no unseen colors. And so like whether it's an out of distribution test set or not, it seems to work fine, and it seems to work fine for robotics. So then here's results for contrastive learning and multimodal learning. Downstream, there's only really downstream contrastive learning, but this is from the CLIP paper. Like this experimental data is straight from the CLIP paper. So just downstream performance on ImageNet after like pre-training on their 300 million, their 300 million, however many images were used for pre-training CLIP. And on the y-axis, the x-axis is how many flops it takes to do a forward pass of that model. So it basically is just linearly proportional to number of parameters. So you could just also have number of parameters on the x-axis. And so it works fine for fitting and extrapolating the scaling behavior of downstream ImageNet when you do contrastive multimodal learning. On the left plot, it's zero shot. On the right plot, it's you have a fine-tuned linear probe. It also works great for uncertainty, extrapolating the scaling behavior of uncertainty estimation and calibration. So this is like a large language model from Anthropic of various sizes. You fit to the first three sizes, and this is like downstream uncertainty and calibration. So like you pre-train the whole internet or whatever, and then the downstream test set is the big bench evaluation from Google that's kind of designed to not be too much on the internet. And so when you have expected calibration error on the y-axis, it models and extrapolates that very well. Here's some extrapolation results for a model that's trying to predict the forces of molecules. So the y-axis is the test force mean absolute error, which is like basically the force is like measured in electron volts per ampere. And the x-axis is training data set size frames, and it's like a graph neural network that's trying to predict the force of the molecules, and it's trained via minimizing the weighted sum of energy and force loss terms. And it seems to model and extrapolate that well. And this is from the Whisper paper. So this is the y-axis in this case is the downstream performance across 67 different languages, across doing audio to text, like transcription across 67 different languages. And then you have number of model parameters on the x-axis, and here's the extrapolation results for downstream audio to text for Whisper. Whisper is basically just a big transformer model that was trained to do just had a big audio to text pre-training objective. Like a really straightforward one too. Okay. So yeah, it also worked. Bergen is also accurate modeling extrapolate the scaling behavior of adversarial robustness. So this is just, you make the model bigger. In this case, they were scaling depth. And yeah, oh yeah. So the adversarial attack they used was projected gradient descent. And yeah, it takes a while to explain that, but it's just a popular adversarial attack method, and it predicts like Bergen neural scaling laws accurate model and extrapolate that scaling behavior too. And the x-axis in this case is flops per forward pass, which is linearly proportional to number of parameters on the x-axis. So you could have also had number of parameters on this x-axis. And then here's some extrapolation results for computer coding / programming. This plot's a little bit special in that in this one, we have fine-tuning data set size on the x-axis instead of like pre-training data set size on the x-axis. So like Bergen neural scaling has also worked fine if you put fine-tuning data set size on the x-axis instead of pre-training data set size on the x-axis. And in this setup, it was a large language model that is like pre-trained on like all the mostly English text on the internet, and then it's fine-tuned on that many characters of Python code. And the y-axis is the test cross entropy on the distribution of Python code, like just on the internet. Like that's just a held out subset of that distribution. Yeah, so it also works fine with sparse models. Like most of the models in the previous slides were dense models that, like Bergen neural scaling it accurately models and extrapolates the upstream and downstream performance of sparse models fine. The upstream, like the top plots in this case are a sparsely gated mixture of expert models. In the bottom plot, it's like a normal dense model, but then the model is pruned before inference to it's pruned before inference to have a 2-4 sparsity pattern. And so like it's still, when you have number model parameters on the x-axis, you still get like a perfectly fine fit and extrapolation, like even if it's a sparse model. You also interestingly can use you can put the upstream performance on the x-axis, which was a little bit surprising to me because like that implies that like a broken neural scaling law of a broken neural scaling law is equal to a broken neural scaling law. And like that kind of drove me nuts for a while why that is, but like there's a really long proof that you can do that shows that actually, yeah, broken neural scaling law of a broken neural scaling law gives you just another broken neural scaling law. So you can put upstream performance on the x-axis too, and you can extrapolate the downstream performance from the upstream performance using a broken neural scaling law, and it'll work fine. Like this is just the upstream accuracy rate on JFT 300M on the x-axis, and then on the y-axis is the downstream error rate on ImageNet, like in a 20-shot setting. Yeah, and it also, all the vision stuff I showed, it works fine if you have compute on the x-axis instead of like the amount of compute used for training on the x-axis instead of like number of parameters or dataset size. And so some people might find that useful to know. There's that recent paper called Beyond Neural Scaling Laws, where they did this data pruning method where like they vary the amount, they vary like so basically the data is pruned Pareto optimally such that each point along the x-axis uses a subset of dataset that yields the best performance, i.e. y-axis value for that dataset size. And when you do their pruning strategy, it just follows a Bergen neural scaling law too, and you can get it like Bergen neural scaling is accurately model and extrapolate that scaling behavior too. And yeah, this is one of the most interesting like plots in the whole paper. So like this is the first plot I'm showing you where the plot has 2 breaks instead of 1 break. So like on the left, like the first descent is like a parallel segment with like one slope, and then you have a break, and then it transitions into a different slope that's going in the opposite direction. Then you have another break where for the second descent part where it transitions into going down again, and just a broken rail scaling law with two breaks like perfectly models and extrapolates that. And yeah, that's on the left plot. And like the x-axis on the left plot could have been number of parameters, and you still get the same result, because in this setting, number of parameters is linearly proportional to model width. And we also have result for training data set size. So finally, this has pretty big implications in my opinion. There is a limit to the predictability of scaling behavior. So right here, so we fit a broken arrow scaling law to, in the left plot, we fit a broken arrow scaling law to predict, like, to fit and extrapolate the scaling behavior of 4-digit addition. Yeah, and as you can see, it extrapolates it well. But we wanted to know, like, say you had infinitely many seeds such that you could perfectly fit the broken arrow scaling law. What is the minimum of, like, what is the minimum of the x-axis values you need to get to if you want to have a perfect extrapolation, even if you have infinitely many seeds? So that's what the right plot is right here. In the right plot, we have infinitely many seeds. So we can perfectly like approximate what the scaling law is, but we're bottlenecked by how far along the x-axis can we go. So basically, like, we have infinitely many points from like 400, data set size 420 and lower. And basically, if you go any lower than that, you won't be able to get a perfect extrapolation anymore. So like that implies, like, if you want to get like a perfect extrapolation, there is a minimum scale you need to have your maximum along the x-axis of the points you're used for fitting to like be, if you want to get a, so like at least with the way the current like method of where you fit a scaling law to a scaling behavior to try to extrapolate it, like there might be some thing where you like look inside the activation, like the weights or activations, and you can get an extrapolation from even earlier if you do that. But if you're just looking at like the raw performance metrics and trying to extrapolate via that way, there is a minimum that you need to get to along the x-axis to get a perfect extrapolation. And this kind of has a few different implications. So like one is there's a minimum along the x-axis you need to get to have a perfect extrapolation. The other implication is, like, if there's an additional break that's sufficiently sharp further along the x-axis, you won't be able to predict where that break happens unless you get like sufficiently close to it. Because like like the full, for example, in this case, like the full scaling behavior of 4-digit addition, it actually has 3 breaks. So like there's a break to the left of this plot, like far to the left of this plot, and there's an additional break far to the right of this plot. And like you wouldn't, like, if that break like far to the right of it is sufficiently sharp, you won't be able to like the signal won't propagate far back enough to where you'll be able to like get any useful information for predicting it. And then the last thing is if you have a break of sufficient sharpness that happens before the points you're using for fitting, like getting more seeds or points before that sharp break isn't very useful for improving extrapolation. So like getting a zillion points that are way smaller aren't that useful if a sharp break happened between the maximum of the points you have and where those smaller points you're getting a bunch of seeds from are. Yeah, and some people might, so that's the main part of the presentation. And there's also like a straightforward multivariate extension for if you like want to vary data set size and number of model parameters simultaneously to because like in all the other ones it was like a univariate We varied things in a univariate manner. Yeah, so any questions?
Yeah, there were quite a few questions.
There were a few
Yeah.
questions, but we're running out of time. So I'll officially end the talk, but people can stay here and still ask their question. But I'll stop the recording. Thank you very
Actually,
much.
yeah, is it possible to keep the recording a bit? Because I think some of the questions, I don't know, there are many, but some of them
Yeah. Okay.
are
Yeah.
recurrent.
Yeah,
People keep asking those. So anyway.
of course, yeah. I'll let it. I'll stay as well. Anyways, it's just that I hope I'll keep on recording even if I leave because I have to leave at noon. So if people keep asking questions, I will have to leave.
Oh, by noon, yeah, we have 15 minutes, so we should be done.
Perfect. Then, like the first question was from Sami initially.
Thank you.
Okay.
Thank you very much, Madame Rich. It was very nice. My question is about the well, in fact, you were trying to capture the complexity of interaction between the parameters, the data, and the model performance by your model. So I guess this was with the power law equation. I guess there might be many ways to improve the power law equation, like maybe developing more sophisticated mathematical models or having more data, or even improving hardware. But according to you, what could be the priorities in the future to improve the power law equation in research? I mean, what could be the most important priority to improve this equation? Thank you very much.
Yeah, well, thanks. It's a very good question. Essentially, what you're asking is how to improve, say, if it is really following just power law, how to improve exponent. And if it is more complicated and it starts following basically broken power law, well, how to improve, say, exponent in a particular kind of region of, say, larger compute and so on. So, I mean, in general, this kind of the question, people trying different things, people trying architectures. The paper that Ethan mentioned about the data pruning was essentially trying to see if kind of selecting samples carefully by ranking which one are more useful and not training on those that are kind of not ranked high, whether it can improve the scaling law with respect to the data. So it's kind of one example of approach. Yeah, so I mean, it's hard to say what exactly may help to improve the exponent or the speed of learning, but it's basically the whole field. Yeah, so but this is, I think my take on that, I think the quality of data really matters, maybe even more than particular changes in the architecture and so on. So again, it was kind of a rule of thumb that people kind of reported, like Jared Kaplan reported on his experiences with GPT-3, that architecture changes kind of mattered a bit less. I think the quality of data or selecting data might be important. Well, hyperparameters are always important, and with scaling, we didn't talk about that. You cannot possibly do hyperparameter optimization at large scale. It's just infeasible. So you do it at relatively small scale. And then good question is, how do you generalize to large scale? Just like a hack or rule of thumb was just to optimize hyperparameters on small models and just keep those hyperparameters for larger models. Then there was interesting work, and I guess still ongoing work on by Greg Young, for example, from Microsoft, on actually proving mathematically what ways of transforming parameters, hyperparameters, would be optimal and stuff like that. I mean, there are many things you can try to improve those exponents, and that's pretty much the whole the holy grail.
Thank you very
scaling.
much. Thank you very much. That was very
Ethan might actually have some better ideas.
Interesting, but I just registered that quality of data is very important. The only thing it brings me another question, but I don't want to take much time about the quality of data, because this is a huge topic, like evaluating the quality of data. Of course, there is the completeness, the consistency, the accuracy, and so on. But evaluating anyway, do you have any scale? Would you recommend maybe an article or a scale to evaluate the quality of data, since it seems to be one of the most important topic? Thank you.
You said the quality of data?
Yes. Is there a scale in research that has been done to?
I mean, you basically just look at the scaling law on all the downstream tasks you care about, and that's how you evaluate how high quality that data is for the thing you're interested in.
I guess that would be empirical. I guess maybe the question is like, is there any metric that you can apply to your data set?
Exactly.
Yeah, because I mean, the extreme case, you have the two data sets. Well, I mean, it's extreme, it's kind of contrived, but say it's a huge data set and it has not much information because same sample or same sentence is being repeated, I don't know, several billion times or something. You're not going to learn much about language from such data, right? But it's contrived example. And the question is like, how do you measure indeed their, I don't know, their information content of the data, so you make sure that it's sufficiently kind of variable or diverse or something, right?
Okay, it's okay. Thank you very much. So there is no metric, but it's just like our experience and our judgment.
Yeah, I mean, there are metrics. It's just I might not think about particular paper link from the top of my head, but yeah, if you send me email, maybe I can. Yeah, I need to look on offline, but I'm pretty sure that maybe it's not mainstream. There are papers on that.
Thank you very much. Thank you.
Okay, next question was from Chris.
Thank you very much for your presentation, Ethan, and thank you so much, Prof. Rich, for your presentation. I have a question about the slide where you show, Ethan, BNSL on Whisper, and you said it's across 6-7 languages.
Yeah.
My question is just basically, so first of all, I'm pretty new to the scaling thing, so I did not really grasp everything about the y-axis as where it's changing. But my question is this: how were the individual performances of the languages integrated, or it doesn't matter here? Because I know that
it's just the mean across all of them. If you want all the details, just look at Figure 6 of the Whisper paper. That's where we get this experimental data from.
I see. Then that brings the next question. So how, so Whisper performs way worse in some languages compared to English. So there are some languages that it got even zero as a score. So when you're doing this prediction and you're using the mean, does it mean that you're leaving out some of these languages, or does it mean that it doesn't become an issue when you with scaling, you're increasing your data set size and no longer becomes an issue? Are you leaving out the effect, the impact on some of these languages?
I mean, I think every single language is going to follow a Berger-Nell scaling law. The more, the more, data points you have, the lower the variance between the seeds is going to be, such that you'll be able to estimate that Berger-Nell scaling law more easily. But yeah, I mean, they're probably going to be following a much worse Berger-Nell scaling law, worse exponent or slope or whatever, because there's just less of it in the data set, if that's kind of what you're getting at.
I see. So that means if I'm interested in a particular language, for example, using the Whisper example, so what I should do is to map a BNSL for that language.
Yeah. But okay. Yeah, I mean, you literally just create a downstream test set for that language, and then you just that's what your y-axis is, the performance on that downstream test set, and then you just evaluate at a few different model sizes or data set sizes, and then fit the Berger-Nell scale out to those points to get the extrapolation from it.
I see. Thank you very much.
Hello. Yes, hello.
Andrew?
Yes. Yeah. Hi, Ethan. Thanks for the presentation. Hi, Irina. Thank you for the presentation too. Kind of a silly question, but how do you choose N?
So in practice, it's pretty rare where assuming your goal is to get the best extrapolation possible, it's pretty rare that using more than one N is useful. It's more useful than just cropping the points before the second break. In practice, the way we find the number of points / the cropping point is basically just you hold out like the last few black points, the last few largest black points, and use that as a validation set.
Yeah.
And then you basically just whichever like number of n or cropping point gives you the best extrapolation on that held out validation set, like that's smaller than the green points. So basically, like in this example right here, you would hold out this like fourth point right here, and you would see like for which value of n, or for like which point where you like crop the where you put like the cropping point or whatever of the min of like the x-axis values yields the best extrapolation on that held out like black point right there. And then that's how you determine it. And then you like bring that black point back in to fit it, and then you get the extrapolation of like the green point.
Nice, thanks. And I guess like if you set the wrong n, I guess like the extrapolation might suffer.
In practice, not really. Usually just
Oh,
what it does
cool.
is it just will like set that break to like you know, it'll set it to just like transitioning into like, how to phrase this. So like in the broken arrow scaling law right here, this C right here is the transition is like how much it's the difference in slope between the previous previous like segment and oh wait, I'm so screen, you can see my screen?
Yes.
Yeah, it's this CI right here. It's the difference in slope between the previous segment and like the current segment. So like in practice, what it'll do is just the parts where like you had too many breaks, it'll just set it, like it'll converge to something to where like that CI is basically equal to 0. So like the slope doesn't change. So it's as if you like had the right number of breaks anyway.
Nice. Okay, cool, thanks.
But I mean, you do have to have like enough points, because like if like, so like in a scenario like I said, like in the whisper scenario right here, like if you have too many breaks or whatever, like it might do like, you know, a squiggly line thing through it and screw things up. But like if you have a scenario like right here where you have a zillion seeds, like even if you have a bunch of breaks, like it's not going to do some wacky squiggly line thing through it, because like, you know, like there's no way to like fit it well if you're doing like a wacky, like you'll get a better fit if you're not doing the wacky squiggly line thing.
Yeah, it's sort of like having a polynomial is just too high degree for the number of points, essentially.
Yeah.
Okay. Thanks. Appreciate it.
Ladislav, you can ask your question.
Hi, I hope you can hear me.
Yep.
So the question was whether there's like any common design principles to these models to actually allow for the scaling to happen, and that they don't get saturated because of some architectural or other kind of issues. And
I mean, they do, everything saturates. So like, as you go to infinity, so like this A in the broken arrow scaling law is basically like tells you like, even if the quantity being scaled goes to infinity, how low can it get?
Right.
Like,
of course, it does get saturated, but maybe I should better say like prematurely saturates because of some bottleneck, bad type of normalization, or
oh
like,
yeah. I mean, the
not
main thing
scaling
is
with
just
depth or with size.
Almost all of them, they'll use like resonance and normalization so that you don't have exploding and vanishing gradients. That's the main thing.
So is there anything like beyond that? And also with I think it was my question was more along the lines of what Irina already mentioned, like the T0 and T5 or whatever was the models from Microsoft. I just vaguely familiar with that, so that's why I wanted to ask whether there's anything more along those lines that allow you to design the models so that once you do have the capacity and you have the few shots at training a massive model or on very large data set, you maximize your chances of observing really good scaling.
I mean, you just gotta Yeah, I don't have anything special to say. I mean, you just kind of got to look at the gradient norms and make sure they aren't exploding and vanishing. So like the
Mhm.
classic example is like transformers, like they scale, like there's a famous plot from scaling laws for neural language models where they show that like transformers, they have like a better multiplicative like offset constant thing in their scaling law because the LSTM, it like the you know, the gradients, they start like exploding and vanishing such that they can't model the long-term dependencies as well as the transformer. So that causes a constant offset in LSTMs of 50x in LSTM scaling law compared to transformers.
Okay, yeah, thanks. I would just like curious whether there is any particular paper that really particularly studies this, or it's more like the knowledge that builds up across the
I guess
literature.
Andrew Brock has some papers from a few years ago that looks at a bunch of like ways to like try to relieve all information propagation bottlenecks. So maybe look at Andrew Brock's papers over the last few years.
All right, yeah, thank you so much.
Cyprien?
Yes, Professor Rish actually answered me in the chat, so maybe I should ask the question on Zoom. I don't know.
Okay.
I can maybe just summarize because you actually
Yes,
raised an
please.
important question. Yeah, the question was, what's our take on federated learning and whether it kind of contradicts or goes along with large model learning? Basically, I answered because, yeah, indeed, in our group, several people used to work and continue working on federated learning. And it's very important area in kind of applications where you just cannot share data. For example, I know that there are efforts here, like Blake Richards is working on that and others trying to build neuro foundation models, which means you need large data sets of, say, brain imaging data. It's unfortunately not possible to collect them, say, all in one place due to various kind of limitations, privacy reasons, and so on, whatever comes from different hospitals. Bottom line, you naturally have to work in federated learning setting where you may want to train one large model, but the data have to kind of sit in different places, and somehow you want to train this model using federated learning algorithms. And the second challenge, which wasn't mentioned in the question, but it's kind of similar, that the ideal case of assuming that you will collect really enormous amount of data in one place, and they will be diverse multimodal, like say Gato setting, the generalist agent that you have, not just image, text, audio, video, but like offline RL data, everything collected at once, and you can start training your model, and it will be all trained at multitask regime, which is easiest way to get like a general model that can kind of generalize from all these different kind of data sets. It's ideal, but not very practical. Say right now, running those projects on Summit, we cannot wait for like 6 months to just collect data set. We want to start training. So we do pre-train on some amount of data, not completely like doing kind of from scratch continual learning. But at some point, from practical perspective, you will have to do also training sequentially on data sets that coming to you here and there. So both issues of how to train large models in this either federated or data spatially distributed or continual data sequentially distributed way to make sure that what you learn is pretty much as good as what you would have learned properly in multitask way. That's a challenge. Yeah.
Okay, thank you very much for your answer.
All right, cool. So thanks again, Irina and Ethan, for this talk, and thanks again for joining us. I wish you all a great weekend, and I'll see you next week.
Thank you.
Thanks, bye.
Bye, everyone.